Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight we are going to continue our discussion on aqueous ionic equilibrium. Specifically, we're going to continue talking about solubility equilibria, which is the topic that we introduced in the last stream 2 weeks ago. By the way, before I go any further, I just want to say for those of you who wished me well last week, thank you very, very much. So basically last week, Halloween, 31st, I was supposed to go live and I wasn't feeling very well. Had some pretty unpleasant headaches, had some digestive problems, to put it mildly. And for those of you who chimed in saying, I hope you feel better and this and that, thank you guys so much. I appreciate it. So without further ado, I will present to you Aqueous Ionic Equilibrium Volume 8. As always, your feedback is more than welcome and highly encouraged, so please feel free to drop your questions, concerns, thoughts, what have yous in the chat if you're watching this live, and if you're watching this as a video, please feel free to leave me a comment, because without your feedback, I am completely and totally lost. So we're going to start this stream off by talking about some of the material from the last stream that was Aqueous Ionic Equilibrium Volume 7. By the way, if you're interested in watching Volume 7 or any of the prior volumes in this Aqueous Ionic Equilibrium live stream series, please feel free to check out my Aqueous Ionic Equilibrium live streams playlist. There's a link to it down there in the description, and if there's any information in this video that you think you are lacking to understand the content of this video, chances are it was covered in a previous live stream, so the playlist would be a good place for you to find that. Got a message from Newman. KTK says, hello, sir. Hello, right back at you, and thank you for joining. So what did we talk about in the last stream? Well, we introduced the topic of solubility equilibria. So way back earlier on in our chemistry education, we learned how to classify ionic compounds as either soluble, meaning they dissolve in aqueous solution, or insoluble, which means they don't dissolve in aqueous solution. And now we kind of understand that that is a little bit of an oversimplification, right? Soluble and insoluble are really just two extremes in a continuum of solubility, and solubility is better described in terms of an equilibrium process. And the example that we used over and over again was barium fluoride. That was one of the examples that we used a lot in the last stream. So if we consider solubility as an equilibrium in which we have an ionic compound reversibly dissociating into its constituent ions, in this case barium fluoride dissociating into barium ion and fluoride ion. Well, if we think about this as an equilibrium, well, any equilibrium process can be described by an equilibrium constant. And the equilibrium constant associated with this solubility equilibria is called the solubility product constant, which carries the symbol K sub SP, so KSP, right? And as it is with any equilibrium constant, it's just simply the concentrations of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. Notice in this case the reactant is a solid, and so we omit that from the equilibrium constant expression. And so these expressions for KSPs are actually fairly simple, right? It's just the concentration of the product, in this case those aqueous ions, raised to their coefficients. So this would be the expression of KSP for the dissociation of barium fluoride, where we have concentration of barium ion times the concentration of fluoride ion squared. And that value for KSP for this reaction just happens to be 1.0 times 10 to the minus 6. And of course, there are several tables, you can find them in your textbook or online, in which KSP values for various ionic compounds are sort of tabulated. You can look them up, right? So if you have any problem where you have to use KSP to calculate something, generally you will be given that information, or you'll at least be allowed to look the KSP value for that particular ionic compound up, right? So we have KSP. We also talked, let me move myself over here briefly. We also talked about something called molar solubility, which is basically just the solubility of an ionic compound represented in units of moles per liter. And you can determine molar solubility from KSP by working out an equilibrium type problem, which is one of the things that we did in that last stream. So if you want to learn how to do that, that would be where you go to find that. So we talked about how to go back and forth. You know, if you're given KSP, how do you find molar solubility? If you're given molar solubility, how do you find KSP? We did an example of each of those. We talked about comparing the solubility of two ionic compounds and how comparing the values of KSP may or may not be a valid comparison. It all depends on this dissolution stoichiometry, right? So if your ionic compound dissociates into the same number of ions, then you can compare those values of KSP to determine which ionic compound is more soluble than the other. But if the dissociation stoichiometry is different, in other words, if those two ionic compounds dissociate into different numbers of ions, then you cannot just use KSP to compare their relative solubilities. So that's something that we talked about. We also talked about the common ion effect, right? So imagine you have an ionic compound and you throw it into an aqueous solution containing one of those ions already. So let's say you have, I don't know, like barium fluoride, and you throw it in a solution that already has some fluoride in it. How would that affect the solubility of that compound? And the answer is it would diminish the solubility of that compound. If you put barium fluoride into an aqueous solution that already has fluoride in it, then that barium fluoride will not be as soluble. It would not dissolve as much as if you just put it in pure water. And we went into pretty thorough detail on that one. And then finally, we talked about the effect of pH on solubility, right? pH obviously is the measure of acidity or alkalinity, H3O plus concentration, OH minus concentration, all that stuff. And so we learned that some compounds are actually more soluble in acidic solution when the pH is low, and other compounds are their solubilities are independent of pH. It doesn't matter what the pH is, you'll still have roughly the same solubility. So that basically sums up all of the solubility equilibria stuff that we've talked about so far in this Aqueous Ionic Equilibrium live stream series. So now we'll talk about the content of tonight's stream. So we're going to start tonight's stream by talking about precipitation. So precipitation, this is something that at this stage in our chemistry education, we should all be fairly familiar with. So just briefly, precipitation is basically when you have two aqueous ionic compounds, you mix them together, and one of the products of the reaction is an insoluble solid, and so it precipitates out. It just forms this solid that comes out of that solution here. So this is an example of a precipitation reaction occurring where we've got some sodium chromate up here. This is aqueous sodium chromate being added to an aqueous solution of silver nitrate. And of course, one of the possible products of that reaction is silver chromate. So you have the silver ion from the silver nitrate pairing up with the chromate ion of this sodium chromate here. And silver chromate is actually insoluble. It would be considered insoluble according to the solubility rules table that we've all seen before, right? But in reality, we understand now that silver chromate isn't necessarily insoluble. Insoluble is just an extreme in a continuum. It really just has a very, very low solubility. In other words, it has a very, very low value of KSP. So we're going to understand precipitation sort of in the context of this equilibrium process that we call dissolution and solubility. And in order to do that, what I'd like to do is I'd like to sort of dig back into our memory banks and go back to a concept called the reaction quotient, which carries the symbol of Q. So this is kind of a concept that we learned back when we were studying equilibrium. And so we have Q, the reaction quotient, and its expression is shown here on the left-hand side of your screen. And then we have KSP over here, and its expression is shown on the right-hand side of your screen. And notice that the expressions for Q, the reaction quotient, and KSP, the solubility product constant, are identical, right? So in this example, we have dissolution of sodium, or it's not sodium, silver chromate. I'm probably going to make that mistake several times tonight where I say sodium, but I actually mean silver. So just brace yourself for that. I'm warning you ahead of time. Silver chromate, right? And so for both of these things, both of these properties, Q and K, the expression is you have the concentration of the silver ion squared times the concentration of the chromate ion. And so you might be asking, well, why do we have two different properties represented by the same expression? And the answer is that this is the expression for KSP, but the concentrations of these ions have to be at equilibrium for it to be considered KSP. So KSP describes this expression at equilibrium, and Q, the reaction quotient, describes this expression under any conditions, not necessarily equilibrium, right? And so if we go to the next slide here, this is just a slide that I kind of took from a previous live stream. We were talking about chemical equilibrium. So this is kind of a demonstration or a graphic representation of how sort of the reaction quotient sort of works. So this is like a simple equilibrium where we have A reacting reversibly to form B. And so the expression for Q would be products over reactants, concentration of B over concentration of A. And the equilibrium constant for this reaction that I made up is 1.86. And so here's sort of how it looks. And so notice that on the left-hand side of this graph, right, this is a situation in which Q is less than K, right? So this is concentrations of A and B on the x-axis and then Q or K on the y-axis. So over here on the left-hand side, we have a situation in which Q is less than K. And so if Q is less than K, then what's going to happen is the reaction is going to proceed more toward the right. You know, more of that A is going to react together to form B until Q is equal to K, right? And on the flip side, if you have over here on the right where Q is greater than K, well, then what's going to happen is the reverse reaction is going to sort of speed up until equilibrium is reached, right? So if Q is less than K, then the reaction will shift to the right towards products. And if Q is greater than K, then the reaction will shift to the left toward the reactants. And if Q is equal to K, then the reaction won't really proceed in either direction because you've established dynamic equilibrium at that point. So the same principle applies to solubility and precipitation, right? So if we go to the next slide here, as I move myself out of the way, so basically what you have is that if Q is, the reaction quotient is less than the value of ASP, the solubility product constant, then what you have is called an unsaturated solution. You have an aqueous solution that can dissolve more ions if they were available, right? So that reaction, in this case, will shift more toward products, and any remaining solid silver chromate, in this case, would be dissolved up until the point where equilibrium is established. Now, if there is no more silver chromate present, then the solution will just remain as is, and those ions will remain dissolved, right? But it technically could have more silver chromate added to it, and that silver chromate would dissolve to form silver and chromate ions, right? That's a situation in which Q is less than KSP. If Q is equal to KSP, well, then this is what we consider a saturated solution. So this has the equilibrium amount of ions in it, and it also has a very, very small amount of solid silver chromate in it, although if you were to look at such a solution, the amount of silver chromate that would be in there, the amount of solid silver chromate that would be in there would probably be so small that it would be invisible to the naked eye. And then finally, if you have a situation in which Q is greater than KSP, then what you have is something called a supersaturated solution, which actually has theoretically, it has more than the theoretically allowable amount of ions dissolved in it. And in most cases in which you have a supersaturated solution, solid will quickly precipitate out of that because the equilibrium sort of wants to shift in the left-bound direction toward reactants. However, there are some situations in which you can actually have a supersaturated solution that does not immediately precipitate, but those solutions tend to be very unstable, and if they are disturbed, then they will precipitate rather quickly. And so it's at this point that I'd like to show you guys a video way back from when I was teaching. So way back when I was teaching, I sort of did sort of a little demonstration like this involving something called sodium acetate. So let me see if I can pull this video up here. So this is like an example of a supersaturated solution. So here, let's take a look at this. Okay, so we're adding a crystal of sodium acetate to a supersaturated solution of sodium acetate. If you will just grab a small amount of the crystal and just kind of slowly drop it in, we can watch the solution immediately solidify.
I think that's so cool.
Yeah.
Boom.
It's so awesome.
Notice that
Now all you have to do is
all of it has solidified, nothing left, no liquid left in that beaker. Instant ice.
It's so cool. Oh my god.
So
And
like
if
if
you
you
add
add
a dye to it,
How do I... Okay, so let me just go back to the PowerPoint real quick. So yeah, that was basically just an example of a supersaturated solution that I was able to prepare. So it was a solution that had more than the equilibrium amount of dissolved ions in it. It really wanted to precipitate, but it has to have some sort of disturbance to actually do that. So the way that we disturbed it was by adding a tiny amount of the sodium acetate crystal in there, and then it just immediately precipitated around that. It just sort of crashed out of that solution, as we would say. It's a very fun demonstration, something that I really enjoyed doing when I was teaching. That was like from 7 years ago. So I'm actually fortunate that I was able to dig back and find that video. So I hope you enjoyed that, because we are moving on with the boring PowerPoint stuff. So, by the way, if anybody finds this stream valuable, if you find my content valuable and you would like to reciprocate and, value for value, so to speak, please feel free to drop a thumbs up on this video. It actually helps a lot. It helps a lot to help people discover this video. And if you're feeling super generous, you can consider sending a super chat, or you can donate through Streamlabs. There's a link down there. I think it's streamlabs.com/benschemvideos. There's a link. It says support the stream. So if you click on that, you can set up a donation. And I think your donation will actually appear on the screen. And I think you can do like text donations. You can type whatever you want in there. Please be responsible about that. So if you're interested in supporting the stream, I would highly appreciate it if you find these streams valuable. And of course, what I really want is your feedback. So if things are good, let me know. If things suck, let me know, or just let me know what you'd like to see on this channel, and I'd be happy to provide that content for you. So got a question from Blair. It says, what happens if you add dye to it? Oh yeah, good question. The dye would just it would just make it wouldn't have any effect on the solubility of the sodium acetate. But I've actually done that before, and it looks cool because you have like crystals like in this green solution, or crystals that form in this blue solution, stuff like that. So I actually have done that before. But in terms of solubility, the dye is pretty inconsequential to the solubility of those crystals. So, all right, so we're going to move on here. So we have a problem here, and I'm going to go into the whiteboard to pull this up. I kind of already have it sort of pasted in there. Look at how ready and with it I am. So we have a problem that says that we got a solution of lead 2 nitrate, and that's mixed with a solution of sodium bromide to form a solution in which the concentrations of lead 2 nitrate and sodium bromide are 0.0600 molar and 0.0158 molar, respectively. And the question is, will a precipitate form in this mixture? Will a precipitate form in this mixture? So this is one of those problems in which we're going to calculate Q, the reaction quotient. We're going to compare it to the value of KSP, and then if Q is larger than KSP, then it will precipitate, and if Q is smaller than KSP, then it will not precipitate. So we have lead 2 nitrate and we have sodium bromide, right? So what we really need to do is we need to figure out what are the possible products of a reaction between PbNO32 and NaBr, right? So we have this lead 2 nitrate, and I'm going to highlight these real quick just so that we all understand what's going on here. So there's the formula for the lead 2 nitrate, and there's the formula for the sodium bromide. So the question is, what are the possible products that we can get from mixing these two aqueous solutions together? Well, one product would be if we had the nitrate ion from that lead nitrate reacting to come together with the sodium that came from the sodium bromide. Now what that compound would be, it would be sodium nitrate. It would be represented by the formula NaNO3, right? But one thing that we probably know, or at least we should, is that sodium nitrate, and indeed all nitrates, any ionic compound that has nitrate in it, is soluble. And so if there's going to be any precipitate that forms in this mixture, it's not going to be as a result of sodium nitrate, because sodium nitrate is highly soluble, right? If it even could be represented by a KSP value, it would be like really high, right? And so we can basically just kind of strike that one off the list. I don't know why there's an arrow there. That's really annoying. Yeah, let me take that off. Okay. So yeah, sodium nitrate, we can basically scrap that on the list. It's not going to form precipitate. But what about the other possible product of this, right? The other possible product of this would be in which you have the lead ion, right, the Pb2+, right? And that would pair up with the bromide, ion from sodium bromide. And so that would be PbBr2, right? Because in this compound here, lead 2 nitrate, the Pb has a charge of 2 plus, and bromide ions, they're group 7a non-metals, they all have a charge of -1, and so you need 2 bromides to balance out with 1 lead, and so you'd have PbBr2. And again, I'm doing this quickly, but at this point in our chemistry education, we should all be able to sort of reason our way through that and determine that this would be the other product. And so lead 2 bromide, right? What's the solubility of lead 2 bromide, right? Well, if you look at a solubility rules table would tell you that this is insoluble or perhaps slightly soluble. I don't know. I haven't looked at one of those tables in a while. But it's definitely not just fully soluble. And so what we need to do is we need to look up the KSP value for this lead 2 bromide. Now, before we do that, what I'd like to do, again, this is something that I just always like to do when it comes to solving problems, is I always just like to write the chemical equation, or in this case, the dissociation equation for the reaction that I'm looking at here. So let's see if I can grab this. I hate this new version of Microsoft Whiteboard. Man, these guys, they really need to do a better job here, because this is just not doing it for me. All right. Well, since this isn't working, I'm just going to write it again. So, okay, so we have this lead 2 bromide. I'm just going to write it in over here, right? So again, like I said, I always just like to write the equation associated with the problem that I'm working on, right? So we have this PbBr2, and of course, that's a solid, and that's going to react reversibly to form the lead 2 ion, so that's Pb2+, that's aqueous, and the bromide ion, or 2 bromide ions, so that would be 2 Br minuses, and that's also aqueous, right? And so allow me to just briefly look up the KSP value for this lead 2 bromide here. So KSP for lead 2 bromide. Again, these are just things that you can Google. You can find them online. You can look them up in your chemistry textbook. And I'm looking it up online right now. So lead 2 bromide, that KSP happens to be, so KSP for lead 2 bromide is equal to, where is it? Okay, 4.0 times 10 to the minus 5. I didn't necessarily mean for this to look like a rainbow. I guess that's what I chose here in this. Anyway, KSP for lead 2 bromide is 4.0 times 10 to the minus 5. Okay, so that's good information. So that means that this stuff is definitely not super soluble, right? 4.0 times 10 to the minus 5 is a very, very small number. And so it looks like there's a decent chance that this will form a precipitate. But again, in order to figure that out, we need to be able to compare the values of Q, the reaction quotient, and KSP, the solubility product constant, and then we can make our determination as to whether or not a precipitate will form in this mixture here, right? And so let me change this to just plain old blue. Okay, so how do we calculate Q, right? So we're at the point where we want Q, the reaction quotient. Well, again, Q is just the same expression as KSP, right? Products over reactants. It's just Q describes the reaction under any conditions, and KSP describes the reaction at equilibrium, right? And so it's just going to be the products. So the products of this are the lead ion here. So we have concentration of Pb2+, right? And then we have that. It's going to be multiplied by the concentration of bromide ion, Br minus, right? And this one is going to be squared because there's a coefficient of 2 in front of that bromide ion, right? And so we were given these values. We were given numerically these concentrations of lead ion and bromide ion. And so really all we need to do is to plug them into this expression for Q and then compare that value of Q to K and figure out whether it's larger or smaller, right? So Q, in this case, is going to be equal to concentration of lead. So that would be 0.0600 molar, because that was the concentration of lead 2 bromide here, or lead 2 nitrate right here. So that would be 0.0600 molar, right? And then what's the concentration of bromide ion? That would be 0.0158 molar, 0.0158 molar. Let's see. Let me fix that. 0.0158 molar, and that's squared, right? And so this value ends up being the result of this calculation right here. So allow me to calculate that real quickly. And if you'd like to follow along with your scientific calculator, that would be cool. You can catch me if I've made a mistake. I actually don't have my scientific calculator with me. I don't know where it is, so I'm using my phone here. So we have 0.0600 times, and then we have 0.0158 squared. 0.0158, and that is squared. How do I guess I can just do times 0.0158. Okay, so I'm doing this in my calculator here. That's a very, very small number, so let me see if I can sort of convert this to scientific notation in my head while we're on the air live. So it looks like we have 1.5 times 10 to the negative, let's see, 5. 1.5 times 10 to the negative 5. I think I did this correctly. Let me just double check real quick. Yeah, 1.5 times 10 to the negative 5. So that is Q, right? And so the question is, how does that value of Q, the reaction quotient, compare to the value of KSP, the solubility product constant? Because remember, if it's greater than KSP, then it will precipitate. And if it's less than KSP, then it will not precipitate. It will dissolve to produce more lead and bromide ions, right? And so 1.5 times 10 to the minus 5, that is less than 4.0 times 10 to the minus 5, right? Because 1.5 is less than 4, right? They're both to the same magnitude. So we can therefore conclude that, let's see if I can do this in another color, since Q is less than KSP, right? That implies that this reaction will proceed to the right, right? If Q is less than K, then your reaction will proceed toward products. And so since Q is less than KSP, this will not precipitate. So the answer then is no. No, the precipitate will not form in this mixture. So really all we did here was we started from the beginning. We identified the possible products, right? One of them was sodium nitrate, which is highly soluble, so there's definitely not going to be a precipitate coming from that one. The other was this lead 2 bromide, which we looked up its KSP value. We determined that it's not very soluble, and so we just figured out Q from the given concentrations using the expression for the reaction quotient, and then we compared that value to the value of KSP to determine whether a precipitate will form or not. In this case, no, it will not. So if anybody has any questions, you are more than welcome to chime in and ask them. Otherwise, we're just going to move on. So let's go back to the PowerPoint where we can sort of move on. All right, so next thing we're going to talk about, and this is going to be a fairly short stream, I think. I don't have much more to talk about tonight. So the next thing we're going to talk about is a pretty cool separation technique. It's called selective precipitation. So chemists have researched and developed a wide variety of techniques over the centuries to be able to separate the components of a mixture. You know, you have liquid-liquid extraction, you have distillation, you have chromatography, you have all these elegant, sophisticated techniques available to a chemist that were invented by very, very brilliant people in order to separate the components of a mixture. And one of them is called selective precipitation. So what selective precipitation is used to do is it's used to separate metal cations, so like sodium ion and calcium ion and potassium ion and lithium ion, and silver ion and mercury ion, you know, those metal cations. You have an aqueous solution with a bunch of those metal cations in it, and you want to separate them from one another, then you would use this technique known as selective precipitation. And so what you do is you throw in a reagent, you throw in some compound into this solution containing a mixture of cations, and the idea is to choose the compound that you put in there such that it will precipitate one of those metal cations. It will form something that is very insoluble, or at least it has a very, very low KSP value compared to the KSP values of all of the other potential products. And so you'll just selectively precipitate it, right? You'll precipitate one of those cations out, and the rest of those cations in that mixture will remain in that solution. So it's a pretty brilliant technique. So let's talk about this in more detail here. So imagine a situation here. So let's say we have this beaker right here, and it's an aqueous solution, and let's say that it has some magnesium ion in it with a concentration of 0.059 molar, and it also has some calcium ion in it at a concentration of 0.011 molar. Now, this is actually true of seawater. Seawater has these two ions, magnesium ion and calcium ion, present in these actual concentrations, right? And so if I wanted to separate, right, the magnesium ion from the calcium ion, how would I do it? Well, as you probably guessed, one method that you could use is selective precipitation. And in order to illustrate this, what I'd like to do is I'd like to sort of take you back to the whiteboard and sort of just kind of scribble this out. So give me a second here. I'm just going to upload the image into the whiteboard. I used to be able to just copy and paste things straight from PowerPoint, but this new episode or this new version of Microsoft Whiteboard just sucks ass. So bear with me while I sort of work out the kinks. Okay, so it looks like I just have the beaker here, but I don't actually have the concentrations of magnesium and calcium in here. So I think I'll just go ahead and let's see. I want to make sure I leave myself enough room here. So I'll put the beaker right there, and I'll just sort of write these concentrations in. So what were they? They were 0.059 and 0.011, right? So we have magnesium ion, so Mg2+, that's 0.059 molar. And we have calcium ion, Ca2+, which is in there at a concentration of 0.011 molar, right? So I have this aqueous solution with these two different types of cation in it, and I want to be able to separate them, right? And so again, what I want to do is I want to put something in here that's going to form a compound with one of these ions that precipitates out while the other compound remains dissolved in the aqueous solution. And one compound that actually happens to work pretty well for this is sodium hydroxide, NaOH, although it would just as easily work well with potassium hydroxide. So what would happen if I took some sodium hydroxide and I threw it in to this solution containing magnesium ion and calcium ion at these concentrations? Well, think about the possible products that could form, right? One possible product that could form would be the magnesium ion pairing up with the hydroxide ion, and what that would produce would be magnesium hydroxide, right? And so if you have magnesium hydroxide, that would be Mg, and that would be OH2, right? So that would be the formula for magnesium hydroxide. So that's one potential product that would form. And then another potential product that would form would be calcium hydroxide, right? The calcium would pair up with that hydroxide ion that you just threw in there. And so that would be the following formula where we have Ca and then OH2, right? And so the question becomes, okay, we have magnesium hydroxide, we have calcium hydroxide. What are the KSP values? What are the solubility product constants of these things? If they are very, very different from one another, in other words, if one KSP value is very, very high and the other one is very, very low, then that means that this sodium hydroxide here is a good precipitating agent. It will force one of these to precipitate, leaving the other one dissolved in solution. Goose says hello there. Hello, Goose. Nice to see you. I think you were among the people who wished me well when I wasn't feeling well last week. So thank you very much for your good wishes, and appreciate you also being here in the stream. So thank you. All right. So the question is, what are the KSP values, right? And so what I'm going to do is I'm just going to drag that down here. And so I'm going to make a column up here for the KSP values, right? So what I'm going to do is I'm just going to look these up. Well, truthfully, I actually have already looked them up. I put them on my wall here so that I don't just choke and not have them available in the live stream. But you could easily, just as easily look these up in your chemistry textbook or just Google them. So the KSP value for magnesium hydroxide happens to be 2.06 times 10 to the minus 13. Very, very, very small number. I got another message from Tharinduni Yuanji. I hope I pronounced that correctly. Apologize if I didn't. He says, hey, hello, right back at you. Thank you for being here, and I hope you find the stream valuable. All right, so the KSP of magnesium hydroxide, 2.06 times 10 to the minus 13. What is the KSP value of calcium hydroxide? Let me look that up. Well, I actually have it written down, and that happens to be 4.68 times 10 to the negative 6. 4.68 times 10 to the negative 6. So this is a small number, right? 4.68 times 10 to the minus 6, very, very small number, but it's much, much larger than the KSP value of magnesium hydroxide. 4.68 times 10 to the minus 6, much, much larger than 2.06 times 10 to the minus 13. And so because there's such a huge disparity in these KSP values, yes, it looks like this could work to separate these two ions, right? So what would happen is, see if I can just use a different, I'll just use black, I guess. What would happen is you would have a bunch of solid that would form in here. It would precipitate, right? And so it would start, I guess, collecting at the bottom of the beaker, right? And that precipitate would be the magnesium hydroxide because it's so lousy at dissolving. It has such a low value of KSP, right? So that would be the MgOH2, right? That's the precipitate that would form, that would crash out of this solution, right? And meanwhile, your calcium ion would largely remain dissolved in solution. Yeah, probably some of it would precipitate out. I mean, after all, it is an equilibrium process, but it would be significantly less calcium ion that you have in this precipitate than magnesium ion. So this would be a decent separation technique. So I don't know. I always like to talk about things like that because I don't know. I just like the clever ways that people have sort of come up with over history to separate the components of a mixture. Some people are really, really, really clever. And so I always just like to share things like that. Very, very simple but elegant solution to the problem of separating the components of a mixture. So, and again, what we're doing here is we're just separating a mixture of aqueous metal cations, right? Selective precipitation, for those of you who just hopped in the stream. That's what we're talking about. And so I've got one more slide for you in this presentation. And it's, let's see if I go back to the PowerPoint here, bear with me. Okay, so we talked about selective precipitation, and one sort of application of selective precipitation involves something called qualitative chemical analysis. And so got this big flow chart here, which I will attempt to explain. So this is basically just a scheme in which selective precipitation is used to determine what type of cations, what type of metal cations are present in a solution that has a large mixture of various different cations. So this is actually a pretty commonly done experiment in like general chemistry labs. So if you're taking general chemistry, maybe you've done this type of experiment before in your lab. Maybe you understood it, maybe you didn't. I don't know. But this is a kind of an old, antiquated way of determining which ions are in a solution. There are much more time-effective, much more cost-effective, much more technologically advanced methods of doing this now, like spectroscopically. But this is a good teachable moment to learn more about selective precipitation and sort of how these differences in solubility can be used to purify something, to separate something, to identify what type of ions are in an aqueous solution. So it's qualitative. We're not really determining the concentrations or the amounts of the ions that are in the solution. Rather, it's qualitative, right? We're determining the type of ions that are in the solution. So basically, imagine, I'm just going to try to walk through this flow chart, and I hope it's big enough so that you can read it. And I also hope that if it wasn't big enough that you would tell me in the chat, but I'm just kind of going to go over this briefly. So up here is like your original solution in which you could have any combination of all of these ions that are present in that solution. And so the idea is you want to separate them. You want to figure out which ions were in your solution. So the first thing that you would do, the first precipitating agent that you would add to the solution would be some hydrochloric acid. So you can add some 6 molar hydrochloric acid. So what would that do? That would introduce a bunch of chloride ion into your solution. And that chloride ion would pair up with certain cations that become insoluble when they pair up, or at least they become very, very, very low solubility, low KSP values when they pair up with chloride ion. And that would include a silver ion, this mercury ion, lead ion. All of those are very, very lousy at dissolving when they pair up with chloride. So if you throw that HCl in there, that provides the chloride ion that's needed to precipitate out these metal ions like silver and mercury and lead, right? And so basically, you throw your HCl in there, right? If any precipitate forms, right, you know it's at least one or a combination of these ions, silver, mercury, and lead, right? And so what you would do is when they precipitate out, you would throw that into like a centrifuge and it would spin around. It would really separate the liquid from the solid portion, and then you would pour the liquid out. You'd have that solid at the bottom of that centrifuge tube, and you would be able to analyze it further if you like. So that would be the first step, to precipitate out these insoluble chlorides. The next step that you would do is you would throw in some sulfide ion in the form of adding hydrogen sulfide. So if you throw some sulfide ion in there, well, that's going to precipitate out a lot of metals that are insoluble when they pair up with the sulfide ion, right? And so that includes a bunch of metals like copper, bismuth, cadmium, lead, mercury, arsenic, antimony, tin. So all of these cations would be precipitated out using that particular precipitating agent. And then the next step is you would have what are called base insoluble sulfides and hydroxides. So these are basically compounds that are soluble enough to remain in solution after adding the hydrogen sulfide, but are not soluble enough after you change the pH of that solution and make it more basic. Then they start to crash out. So that would include like your aluminum that would precipitate in the form of aluminum hydroxide, iron that would come out in the form of this iron 3 hydroxide, all the way over here where you have like cobalt, manganese, they come out in the form of sulfides, and then everything else in your solution is either a group 2A metal, like an alkaline earth metal, an alkali metal like sodium or potassium, or ammonium. And so at this point, what you would do is you would add this stuff right here, NH4,2-HPO4, that's diammonium hydrogen phosphate. And so when you throw that in there, what that's going to do is that's going to precipitate out all of those alkaline earth metals, right? Like your barium, your calcium, your magnesium. Those are all going to precipitate out. They're going to bind to phosphate, and they're not very, very soluble in that form. And so they'll precipitate out. And then finally, what you're left with at the end of all that is, your alkaline metals and ammonium, right? Your sodium ion, potassium ion, lithium ion, whatever, and ammonium. And those, you're not going to be able to precipitate those because there is no anion that these group 1A metal and ammonium cations can pair with that's going to cause them to precipitate. They are soluble in everything. And so you would have to find some other method to confirm the identity of those ions in your solution. So one of those is called like the flame test, where I'm sure you've seen that before, where you put like you burn it in a flame, and in the case of sodium, it'll show up like orange, yellow flame. Potassium, I believe, you put that in there and it shows up at this like purple, like violet flame. So that's one qualitative way to figure out what kind of metal cations you have in your solution after all the rest of them have been precipitated out. But that's just something that I wanted to talk to you guys about. Again, maybe in your lab, like the lab component of your general chemistry class, you might do an activity like this, you might do an experiment like this. And if you look at this flow chart all at once, it looks a little intimidating, like, whoa, what the hell's going on here? But it's actually pretty straightforward, right? You just throw in a precipitating agent, and that crashes out a specific class of cations. And then you sort of separate them and take them away. And if you see any precipitate, well, I know at least some form of these ions were in my original solution to begin with. So, okay, everybody, I think that will do it for this stream. And actually, that will do it for this topic. That's right. Aqueous Ionic Equilibrium is now finished, right? So we're going to move on. We're going to move on to another topic starting next week. So when is that going to be? That's going to be next week. That would be the 14th, right? November 14th. Next Sunday, we're going to start a brand new topic. I have a topic that I kind of want to start discussing, but really that's up to you guys. If you guys can think of another topic that you would like to discuss, we've done chemical kinetics, we've done chemical equilibrium, we've done acids and bases. Now we've done aqueous ionic equilibrium. So we got to keep this train going. So the more feedback I get, the more informed decisions I can make in terms of where to go next. I really, really, really love and need having your guys' feedback. So I appreciate any feedback or criticism that you want to sling my way. It's been fun doing aqueous ionic equilibrium. Some of it's been pretty challenging, like all these titration calculations. And it seems like every other week or so, my daughters are bringing home some germs and and making me sick, so I've had to cancel streams, but it has been fun. I've been enjoying doing these live streams, and I hope you've been enjoying consuming them or watching them. So, All right, everyone, that is going to be it. Again, thanks so much for joining me tonight. I look forward to seeing you in the next live stream. And oh, I guess one more thing is I should announce, I sort of announced this already in a video that I published, like a YouTube short video that I published earlier. But basically, the time that I stream on Sundays has kind of changed because we have exited daylight savings time and we have entered standard time. So that involves setting our clocks back by an hour. And so the time zone technically has changed. So instead of Eastern daylight time, which is what we were in yesterday, now we are in Eastern Standard Time. So Eastern Daylight Time, that was the UTC -4. Eastern Standard Time is UTC -5. So it doesn't make much of a difference for people who are here, like in the US and in Canada, like North America. The time zones are basically the same, or at least the daylight savings schedule is still the same. But for people in other countries who don't follow, that might be a little confusing. So yeah, my new stream time is Sunday nights, 9 o'clock p.m. Eastern Standard Time, which is UTC -5. Thank you all very much for joining me. I hope you've had a great weekend. And I hope you are all set up to have a great, wonderful, awesome, productive week. I will see you in the next stream. Later.